Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense system's DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
Well, good morning, afternoon, evening to everybody who has joined us. Thank you so far for taking part in this webinar. I'm excited to have Rob give this presentation. Before I hand the mic over to him, so to speak, I wanted to give a couple pointers for logistics of the webinar platform. First thing I wanted to direct everyone's attention to is that if you are in the online browser platform for any meeting, up at the top middle of your screen, you should notice a little icon of a chat bubble. If you click that or hover over it, you should see some description of audience questions. At any time during the presentation, if you have a question that you would like to ask Rob, you can submit that question. And what we'll do is we'll compile a list of questions, and at the very end, we will have a little Q&A session and go through those questions in the order that they're received. So again, at any point during the presentation, just go ahead and type up your question, enter it there, and get it in queue. And I do want to just quickly distinguish that audience question section from the chat feature. You'll also notice, I think on the left-hand side, a chat feature. You can that's for interacting with us if you need to get in touch with us for one reason or another. But if you do have a question that you want to submit to Rob at the end, I would encourage you to put it to the question portal, not in the chat. Beyond that, just will mention that if you have any technical difficulties, you can always dial in. So you should have gotten the dial-in information when you registered, and you could always download the slides, which are available on our website, and just follow along that way. And then the final fallback is that if all things fail, we are going to be recording this and making this available, so you can always catch up with the recording later on if you need to. And I think that covers the bases on everything. I'll just encourage you, as we went through that little introduction video, to go to the website, learn more about DSIAC, who we are, what we do. Providing these webinars is, as mentioned there, one way we try to get the word out on some great work the DoD is doing. And so to that end, I'm excited to have Rob here. Thankful for Rob to spend the time going over the work that they're doing out at ARL and this new simulator that they have. So Rob, I will hand the mic over to you, and you can carry on. I'll chime in at the end for the Q&A.
Okay, thanks, Brian. I really appreciate the invite and the opportunity to present in this venue. It still feel like saying good morning this soon after daylight savings time, but good afternoon, everyone, and thanks for joining this webinar. My name is Robert Kargas. I'm a mechanical engineer at the Army Research Lab at Aberdeen Proving Ground, and I have about 15 years of experience in the field of occupant safety, mechanical shock, and blast protection systems. I'm primarily an experimentalist, and I'll be presenting some unique experimental capabilities that have been developed at our lab, I guess beginning around 2009. So with that, I'll describe our technical problem. When I joined in 2006, the underbody blast problem was very pressing. We were seeing these types of engagements in both theaters of war. And of course, there was a historical basis for it too, but the development of mine-resistant vehicles improved significantly, and it was because a lot of the study and effort put into understanding this problem of buried blast, the blast structure interaction, and our aspect of it in particular was what we call the secondary blast effects. So these would be the response of structures subjected to blast and the effect that that structural response would have on the occupants inside of the vehicle. So we partnered with Lansmont Corporation, which had a great deal of experience in laboratory shock equipment. They kind of cut their teeth on drop tower testing, and this was kind of the gold standard for doing all sorts of transient shock testing for, say, logistical hardness or fuses and munitions. And it was a natural extension to leverage their experience to produce equipment that could test to a different shock specification, such as the one that we see in underbody blast. We're going to call this first machine that was procured the first generation simulator, also known as crew seating blast effects simulator, as it was designed to test and develop blast resistant seats. It's vertically oriented, stands about 35 feet tall, and it can impart an acceleration to a test article and reach a velocity of about 9 meters per second. It can execute the liftoff, which is the initial upward motion, and also the subsequent slam down effect that would occur as the vehicle returns to ground. An additional unique feature of this machine is that it had an independent propulsion system that could impart a different motion to the legs of the occupant. That secondary system would produce an amplified velocity of up to 15 meters per second. And the reason for that is that is typical of underbody blast response. The floor would typically see the highest motion, followed shortly thereafter by a reduced or lower frequency motion at the seating attachment location. There are some animations in this slide deck, and I will point those out, but I don't believe they will play in this presentation mode. So the slides which are available to you, you can go back later and view those, but I will do my best to point them out. So going back to the actual field events to which this machine was developed, it became pressing to understand where the injuries, and when I say injuries, I say assessed injuries, because we don't have real-time data collection in theater. It was field experiments and the dummy responses from those experiments that allowed us to determine where in the total underbody blast picture these injuries were occurring. And the need was to focus our laboratory simulation capabilities in that regime. So after the soil reaches the target, we begin to see structural response. So this is that motion that was referenced in the prior slide as the motion to the lower legs. Soon after, rigid body motion starts. The vehicle has left the ground at this point. Over a short duration, it will reach its maximum velocity, have a ballistic trajectory, reaching max displacement, and then ultimately returning to ground. Now, I believe there was an old SLAD study on this that looked at where these injuries are occurring, and the predominance of them is in this early phase of the event, anywhere from 5 to 90 milliseconds in. Now, these were likely the maximum or the highest injury severity responses, while slam down typically would rank lower. Go to the next slide here. Taking a closer look at some of the response data from those field experiments, the vehicle structure response to blast is typically bimodal, and by that we mean it appears to be two different distinct waveforms. One is the initial response due to soil hitting the underside of the vehicle, and the second is the lower frequency, or what we call rigid body motion, where everything picks up and moves in unison and leaves the ground. First generation simulator focused on this global effect. This black trace here is actually an isolated response on the cab of the vehicle. The other traces represent inputs and solid curves to the seat. And in the dashed curves, we have the response of the seat. And the seat would be an isolated system, so it would attenuate a great deal of that energy. This chart showing velocity versus time exceeds 15 meters per second, and this far exceeded anything that we would be able to reproduce with the first-gen simulator. So it became pressing to have a way of producing this type of motion in the laboratory, this bimodal response. And so the second generation machine was developed. At lower left, there's a model animation showing this effect on the cross-section of a generic hull. So here in a nutshell is an early rendition of the second gen blast simulator, and it's very similar to the first generation machine in the means of propulsion, how the pulses are modulated in both duration and amplitude. But what is different about them, or this machine, is the presence of these arrestor masses shown in brown on the sides of the test platform. Beneath the test platform is the propulsion system, which drives what we call a bullet into the underside of the test platform. And then beneath that are the gas cylinders that propel the bullet. Talk a little bit about this momentum exchange principle. The arrestor mass shown at top here has an adjustable mass. There are mass plates on it that can be added or removed to provide the needed residual velocity to the test platform. So what we have here is like a collision of billiards, or a Newton's cradle type concept, where the test platform represents the mass in the center. At right, we have acceleration, velocity, and displacement for the test platform. The initial waveform in red represents the motion occurring after, or during the interaction between the bullet and the test platform. There's some separation, and then the test platform interacts with the platform arrestor, producing a restoring pulse. So here's one mode, here's the other. When we put those together in velocity, integrating in time, we see a high initial amplitude followed by what takes over as a lower rigid body response. Now the scales are different here, but this is more like the actual field experiment data that we saw in a prior slide. This here is an animation that was generated, or not an animation, an actual high-speed video. It was generated recently at acceptance testing of the second-gen simulator. We had initially installed the machine back in late 2019, but due to pandemic-related restriction, we had a great deal of delay in getting it qualified up to its maximum performance, but I can say now that that has been done. What we would see here is the bullet mass rising upward, striking the underside of the test platform. The test platform would move through some distance of several inches before it contacts the elastic programmers on the underside of the arrestor mass. These programmers are adjusted to produce the pulse durations needed for any given experiment. On top of the test platform is a 600-pound just ballast mass to represent the maximum payload on the test platform. And we were able to achieve 20 meters per second at a duration of 5 milliseconds. I believe that was shown in the prior slide. Sorry, 10 milliseconds in this case. I'll talk now about another specification for the second-gen simulator, and that was its ability to tolerate or simulate transverse loading to a test article. As the underbody blast environment is rather chaotic, not all of the motion imparted to a seated occupant is necessarily vertical. The left side of the slide has an animation showing the degree of transverse motion that can result from an underbody blast. What we would see is a stress wave traveling through the structure, causing sponson wall to move outward and inward. We know this has a significant effect on occupant response because occupant position itself has an effect on occupant response. And in this case, the occupant would move forward with respect to the seat, causing extreme cantilever loads to the seat pan, and the seat itself would collapse. The ability to simulate this in the laboratory was envisioned, so the second-gen simulator featured a much more rigid linear bearing system to constrain the test platform. And the way we would deal with this, or producing this motion, would be through the use of dynamic test fixtures, and I'll get into that in a moment. Imparting transverse load where using a uniaxial machine requires either an independent propulsion system, of course would take away from the payload budget that the machine has, or some sort of induced motion as a result. And in this case, we have a 4-bar linkage system with an energy attenuating mechanism spanning one of the bars. What this does is imparts a transverse motion in the plane of the upper plate simultaneous with a vertical motion as the test platform moves upward. This may be useful in the testing of floor-mounted seats in which the insults measured really can't be ignored in transverse direction. Similarly, where seats may be wall-mounted, this 4-bar linkage system can be repositioned. Essentially, it's been rotated 90 degrees, and a wall-mounted seat could be attached to it to produce the inward-outward motion of the hull wall. So we saw an animation in finite element. Let's look at an actual field experiment in which we have a simplified hull structure. This is just a box, a reinforced box in which we have seated occupants installed. This plot at left shows this is actually a spatial plot, and the time history is occurring between the dots. So we have from 0 to 50 milliseconds for 3 different instrumentation locations. So the left wall, positioned here, trace in the center is on the back wall. and the trace at right is on the right wall. What we're looking at here is the displacement over this range of 0 to 50 milliseconds, and we see that same inward-outward motion in the wall. And using that 4-bar linkage fixture, this is an animation here. I encourage you to go and view this. You can see that motion can be replicated using the upward motion of the test platform. So you could have a seat mounted to this face of the fixture. And the dynamics of this are, of course, determined by the characteristics of the shock absorber and also the arm, the 4-bar or the bar linkage length. We have a dynamic model that can be a parametric model that can be used to tune to any pulse, so pulses can be simulated in advance of experiment. And in the floor-mounted case, this also is an animation showing a finite element model of the 4-bar linkage fixture undergoing some transverse displacement as a result of the vertical motion of the test platform. To date, we've done some experimentation with the vertical 4-bar linkage system, and in this case, we added a sacrificial plate. So this particular plate wasn't intended to mount a seat to, but was intended to produce a similar strain environment to that seen in structures subjected to UVB. These are animations as well. What you would see is this plate being induced into buckling as a result of the upward motion of the test platform. Reasons for doing this may be sensitive equipment mounted inside the vehicle. It may not, the blast environment is harsh for a number of reasons, not just to occupants. This motion was simulated as well in the laboratory. This happens to be the older first-generation machine, but the fixtures are extendable to across any type of apparatus. This fixture was, of course, modeled in Ellistina. What we're seeing here are two animations that show some early development that was done in cooperation with Landsmont of, what kind of dynamics would we expect given this design. Some aspects of that fixture you saw on the previous slide have been removed to make this visible. I encourage you to take a look at the animations to see what is going on in the sequence of events that's occurring. Here we have further animation showing the what we call the kick loads or resistance to kick loads imparted by transverse loads. As I mentioned, the second generation machine is much more rigid than the first generation machine, which had only 2 guide rods at the left and right of the test platform, second gen having 4. So it resists kick loads much better. All right, so as I mentioned, this machine has just become fully operational. It has not been used currently to do any sort of retrospective analysis of blast-resistant seats that were developed on the first generation machine, but that's something we'd like to do. I'd say now we have a much better equipped laboratory for representing both global and local motion effects to blast-resistant equipment. The mechanical fixtures for introducing transient shock components in non-vertical directions, those are currently, they've been designed but have not yet been built. We were expecting operational status back in 2019. So some of you may have heard of this machine prior to now, but the significant delays have pushed that back until present. in the Soldier Protection Sciences branches at ARL, we have the ability to do PMHS specimen testing. However, in this particular laboratory, that's something we still need to add. And we're eager to support any kind of, I guess, further development or improvement to blast-resistant equipment. Excuse me. I should give a nod to the people with whom this project first began: Ami Friedman, ARL retired, and Dean Lee. This effort was co-led with the Office of Naval Research, Rodney Peterson, who has since retired, I believe, Jeff Bradle, Howie Drayson, Maureen Foley. Neil Janosdowski was instrumental in getting this equipment moved up to its current location at the Aberdeen Proving Ground. And also the folks at Lansmont who were eager to take this project on despite some of the challenges with the severity of this shock. So I encourage you to reach out to me or someone else in the Soldier Protection branch, or if you're ever at the Aberdeen Proving Ground and would like to see this equipment, let us know. And that's all I have, Brian. Thank you.
Yeah, no, thanks, Rob. That was great. We'll now transition to kind of a Q&A time. If anyone does have any questions, I kind of refer you to the top middle, should be top middle of your screen. You can submit a question for Rob. I'll throw it out just to kind of get the ball rolling, which is to ask for your system, Rob, do you guys, if anyone wanted to come and do some testing there, do you have an ATD or dummy that you can use, or would someone have to bring their own?
So we have a suite of hybrid 3s in the 50th, 50th, and 95th percentile sizes. The Wieman dummy, which is the Army's new or the updated surrogate device for testing, that's a little bit harder to come by. We have access to them through the Aberdeen Test Center, and I've used them in the past, most recently about 6 months ago. But we require ATC support at this point in order to use the Wieman dummy.
Gotcha. Okay, so folks could borrow the other dummies you have available for their testing.
We do, yeah.
Good. All right. Thanks, Randall, for submitting questions. So we got one here from Randall. The question asked is, do you use any CFD modeling to inform the distribution of forces on the vehicle during the blast?
So I guess this is referencing what we, I guess, would call the primary blast response. Is that correct, Miles or Randall?
Well, him not being able to respond directly, well, I think we'll have to take that assumption until we hear otherwise.
Okay, but yeah, I would say personally, I do not do any of the blast structure interaction itself. I kind of focus on the other half of the picture, which is structure and occupant interaction response.
Right. He did. Yeah, he sent another question that's just confirming yes, that's what he's interested in. Oops.
Oh, okay. I see. You responded. Got it.
Yes, there you go.
Okay.
All right.
Nice.
And we did get a comment from in the chat just over to us saying that blast structure interaction was invested in by BP3I in 2011. And AL3D, Lawrence Livermore's NAT code, they can do coupled blast, underbody blast problems.
Right. I feel that a question by it was a representative for a company using a code called Impetus, who had a similar question regarding this. And a lot of the I guess the end-to-end simulation, or what we call primary, secondary, tertiary simulation of the UBB events, is really encouraging, and it seems to be very powerful. and is of course not subject to the limitations that we have in the laboratory. But this equipment is very useful for generating model validation data, where those models need to be, some surety is needed in their response.
Absolutely. All right, we go to the next question here. We did get a couple more filed in. So the next question, Rob, for you says, do you all perform research internally, or do you ever write SBIR solicitations to seek external help?
SBI, I have not written an SBIR proposal or sought a or generated a BAA associated with this equipment. One thing that I think is of interest that I could imagine doing that for would be non-standard uses or extended applications of this shock equipment. There are, within the shock test community, I guess there are some companies that have a lot of history developing equipment, MTS, Lansmont, etc., and the use of shock amplifiers to produce, extreme shock environments, an order of magnitude or more greater than what we're currently doing, seems attractive, because these machines, in a general sense, are just really large propulsion systems that can be extended into, extreme acceleration environments for smaller test articles that may have nothing to do with occupants. So in that sense, we had fielded some questions about unique shock specifications for munitions for which there are really no machines or laboratory capabilities to do them yet. So I could imagine an SBIR could be helpful there.
Yep. Yeah, very good. Let's go to the next question. Next question simply asks, how long does it take to set up and run a test?
Okay, in the current laboratory, we're able to generate our own compressed nitrogen, and these machines, all of our shock equipment runs either on gravity or compressed nitrogen. And in the case of this second-gen simulator, which uses nearly a full nitrogen bottle for each shot, we're really only waiting for the time to vent the gas, and we can do several in a day. Now, the complexity of the test setup is the unknown there. And positioning a dummy, replacing seats, evaluating data, that's really where I think the time between tests can vary.
Okay. Very good. And maybe follow-up question: how many folks would be, humans would be involved in trying to set up and run any given test?
It's a minimum of 2 for safety reasons. But like when we have ATC supporting Weeman use, we would have someone there to support the dummy. It would probably be myself and a technician. As far as the laboratory space itself, we can accommodate, I'd say, around 10 guests or so, or visiting personnel to witness tests.
Gotcha. Okay. All right, Rob, next question is asking if there's a validation report that compares live fire test data to your simulator.
Okay, a validation report. So I don't want to misuse the term validation, Brian, because I know in the world that you came from, that has a very specific meaning.
Right.
I think you're referring to, do we have a good side-by-side comparison of not just response from structures and response from this simulator, but in the ways that are meaningful, our occupant responses more closely match to what we see in the field? And if that's what you mean, that's something we hope to do now that the machine is qualified. So I would expect that in the next 6 months.
Gotcha. Were there Were there any requirements for that were requirements for the machine based on live fire test data, saying it needs to have this sort of response for the ridge motion or the immediate response, that kind of thing?
So I guess the requirements for the machine were heavily weighted toward the just the velocity potential.
Mhm.
I guess it would have been around, 2010, in which UBB events in theater seem to be increasing um, in scale. Like the threat levels were quickly began to exceed what we could reproduce in the laboratory.
Right.
So that was really the driving force behind the development of this second gen machine.
Okay. So the plan or hope is that now that the machine's ready to be used, it can be run, data can be extracted and compared to what is measured from live fire test data.
Right. So I think what that would mean is to you know take an LFT event on some vehicle, set up the same occupant and seat system on this second gen machine, you know, um, match or generate the same or generate a like input, and then see if our responses are closer, or where do they fall.
Yep, that makes sense. All right, very good. Let's go to the next question we have. This question is effectively asking what the maximum payload is.
Okay, maximum payload for the second gen machine is 600 pounds. And that number is kind of fuzzy. It just means that you cannot expect to get the velocity of 20 meters per second if you have more mass on there than that. Similarly, an unloaded platform will reach that peak velocity at a much lower pressure. So that payload of 600 pounds was a number that generally represented the mass of a seat, fixture, and ATD.
Mhm. Got it. Okay. All right. Next one we have here is asking, so if we already have a currently fielded system that's undergone live fire testing, and you've got good floor, hall, seat input data, is the fixture able to be modified to match those characteristics?
Um, yeah, the fixtures they currently exist as parametric models, and they were kind of intended to do just that. So you could simulate, if you've got a reference pulse to which this fixture can be tuned, then you could, determine that a priori and then have it built. Am I understanding that question correct?
I think so, right? I mean, if you've got floor data that's giving you certain velocity, certain you know time, and then kind of hall data or input to the seat from a test that's giving you kind of a different one, can you tune your machine to replicate that?
Yes, I mean, ideal replication is probably not possible because a lot of the waveforms we see in blast are, I guess, a bit noisy, and this machine produces what we call ideal Haversine type pulses. So some, I guess, some approximation of it is required.
Mhm. Right. So you're going to have to take some live fire data and sort of convert it, so to speak, in something that's meaningful for that the machine can actually replicate.
Correct. Yeah.
Okay. Um, any other questions? Oh, here we go. The next one. All right. Next question is about V hulls, which might not be Well, saying, have you noted that a V-hull with a crushable external surface needs to be coupled with the blast resistant seat in order to save the crew members, which maybe goes a bit beyond
Um,
this, but go ahead.
yes. Okay. Now, I guess the V-hull being um, the V-hull is, I guess, an attempt to interfere with the um, or to influence those primary blast effects and what might happen as a result of that.
Hmm.
V-hulls, I guess, I guess it's possible to overmatch any vehicle. If you had an infinitely stiff hull that did not deform in any way, well, that energy would have to go somewhere, and you'll probably get it in the form of rigid body motion. So this vehicle could be sent to the moon, practically. Um, so there are, I guess, competing philosophies. Do you want uh, how much of the blast energy do you want to get coupled to the vehicle, and where and how quickly? Like, how localized do you want it to be versus how globalized do you want it to be? Um, Brian, you worked with um, I guess field experimentation a lot. What have you heard about VHALs, and if they're, are they fundamentally useful, or do they just uh, is the trade-off between distance and standoff with blast make it kind of a moot point?
Yeah, I mean, it's always there's always a good engineer. You're going to say it depends. It depends on where that blast is going off, and how the rest of the structure is going to be coupled to that hull as well. I mean, the shape that it has is designed to kind of transfer loads in certain ways. So it could be advantageous to have a crushable external surface around a V hull and then have it coupled to a seat that is further kind of reducing the blast. But that could also be, more dangerous that you're coupling together something that's exposed to the outside of the vehicle to ultimately something that the occupant is seated in. So I could see that as being something a little bit more dangerous. But again, there's so many other design factors involved, so it's hard to say for sure. And I will just caveat too that I think, relative to your presentation, I don't. It would be difficult to kind of capture all of that. I don't think you can capture any of that in the simulator you guys have built.
Right. I would say, a V-hull probably affects the appearance of the reference pulse that would come from that structure.
Right.
But as for their efficacy, I think we all accept that they're good under ideal conditions in which charges are placed right where they need to be to make it advantageous.
Yeah, exactly.
Yeah.
All right. I think we've commented that as best we can in this setting. I think that is all the questions we have at the moment. If there, I'll kind of try to fill the space for a moment or two and see if there's any other questions that folks want to submit. Again, it's a little chat dialogue or chat icon that's in the top middle of the screen. What I will say, as Rob has here on the last slide, if you do want to get in touch with him, the contact information is there. It's also, the slides are available for download from the DSIAC webinar under this webinar's webpage. And so you can get in touch with Rob directly, or if you have any questions you'd like to have us, DSIAC, explore for you, we'd be happy to do that with our technical inquiry research service. So be sure to check that out as well. I think that'll wrap us up.
And, yeah, contact me. I have fact sheets on the other shock equipment in that laboratory for dissemination. If any of you are interested, just reach out.
Oh, you know what? Before we depart, I did get one question just submitted here at the very end. So we can comment to this one, Rob. Has any thought been given for optional manned vehicle and unmanned vehicle survivability work?
Okay, I guess being an occupant safety and soldier protection group, I can't say I've worked with any unmanned vehicle systems or or vehicle systems that have the potential to be unmanned. A lot of the concern goes away for vulnerability, I guess, in that sense. But I think the loss of an asset is a sufficient reason to keep survivability as a goal. Are you referring to unmanned ground vehicles? Because I would say that, this is shock equipment that's general in nature, and the shock environment isn't limited to buried blast or even ground vehicles. Where there's a shock specification that requires transient shock of the type we produce, I don't think it would matter if it's require or if it's a manned or unmanned vehicle.
Well, and kind of a follow-on question submitted is maybe if you could comment on using your simulator for equipment inside the vehicle. We've talked a lot about occupants, but any reason that the equipment couldn't be placed onto the simulator?
Right. I see what you mean. So sensitive equipment such as munitions, electronics, I'm assuming you mean that sort of equipment. And I think MIL standard E10 encompasses a lot of the test methods for that. And yes, of course, this equipment is useful for that as well. As far as any new or emerging equipment, in the past, we've done a lot of work with munitions and fusing. So, yeah, I'd say the answer is yes. That's definitely an advantage of this laboratory.
Good. All right. Well, thanks for sneaking that question in here at the end, Jeremy. Glad we got time for it. All right, Rob. Well, thank you for your time, presentation, and for everybody else for joining us. I appreciate it, and hope you have a great rest of your day.
Okay, thanks all.